This video will cover a solution guide to problem 66 from chapter 6. 5 kilogram package slides 2.8 meters down a long ramp that is inclined at 23 degrees below the horizontal. The coefficient of kinetic friction between the package and the ramp is 0.310. Calculate the work done on the package by friction, the work done on the package by gravity, the work done on the package by the normal force, and the total work done on the package. If the package has a speed of 2.2 meters per second at the top of the ramp, what is its speed after it has slid 2.8 meters down the ramp? The strategy here will be drawing the picture described in the problem, extracting a free body diagram from that picture, defining all the forces acting on the package, and figuring out which forces will actually do work on the package. As you may be able to tell from the picture, the conventional horizontal and vertical coordinate system may be a bit tricky to work with. So what we are going to do is tilt our coordinate system so that the x-axis runs parallel to the surface of the ramp and the y-axis is perpendicular to the surface. It may not seem obvious right now, but this will simplify our calculation further on. The normal force is upward in the positive y direction. The force of friction is opposing the package's motion and points to the left in the negative x direction. And the force of gravity is pointing straight towards the ground at an angle of 23 degrees to the right of the y-axis. So let's start by splitting up our forces into x and y components. There are 3 forces acting on the package: the normal force, the force of friction, and the gravitational force. In the coordinate system we've set up, the normal force does not have an x component and is therefore entirely acting in the y direction. The force of friction behaves oppositely. It has no y component and is therefore acting entirely in the x direction. Because gravity always pulls an object straight down regardless of the angle of the surface it may be resting on, gravity will have both x and y components in this situation. It will have an x component of mg sine theta and a y component of negative mg cosine theta. As we've done many times before, we can write out the total force equations and set them equal to the mass multiplied by their respective components of the acceleration. Because this problem is asking us for the work done, we really don't have much use for the x direction summation of forces. However, because there is no movement in the y direction, the summation of forces in the y direction tells us that the normal force is equal to the y component of the gravitational force. We can use this later to calculate the force of friction. The definition of the work done by a force is the magnitude of the force multiplied by the distance and then multiplied by cosine of phi, where phi is the angle between the direction of the force and the direction of the displacement. Because of the way we have chosen our coordinate system, the cosine of phi calculation becomes very simple. If the force is acting parallel to the surface, phi is equal to 0 and causes cosine of phi to be 1. If the force is acting anti-parallel to the surface, phi is equal to 180 degrees and causes cosine of phi to be negative 1. And if the force is perpendicular to the surface, phi is equal to 90 degrees and causes cosine of phi to be 0. What this tells us is if the force is parallel, work is positive. If the force is anti-parallel, the work is negative. And if the force is perpendicular, the work done is 0. So let's start calculating the work done by our 3 forces. Part A asks for the work done by friction. The work done by friction will be negative due to its anti-parallel orientation. Because work's definition uses the magnitudes of force and displacement, we don't need to worry about the signs of either of these. The positive or negative sign for the work done by each force will come from the cosine of phi. Plugging in the values we were given, we find that the work done by friction is negative 39.2 joules. The work done by gravity will be equal to mg sine theta. We only take the x component of the gravitational force because the y component will be perpendicular to the package's motion and will therefore do no work on it. Plugging in our values for m, g, and theta, we find that the work done by gravity is 53.7 joules. The same argument for the y component of the gravitational force applies to the normal force. Because the normal force is completely in the y direction, it will do 0 work on the package. The total work is simply the summation of all the work done by the individual forces. Adding up the values found in parts A, B, and C, the total work done on the package is 14.5 joules. Part E wants to know if the package was moving at 2.2 meters per second at the top of the ramp, how fast would it be sliding right at the bottom? Another definition for the total work done on an object is the difference between the final and initial kinetic energies. We want to know how fast the package was moving at the end, so let's rearrange this equation to solve for the final kinetic energy. Substituting in the definition of kinetic energy, we find that 1/2 mv final squared is equal to the work done on the package added to 1/2 mv initial squared. Solving this equation for final velocity and subbing in the values for our variables, we find that the block was moving at 3.26 meters per second at the end of the ramp. Conceptually, this makes sense. In part D, we found that the total work is positive. Because work is defined as the change in kinetic energy, which is equal to the mass multiplied by the change in the squares of the velocities divided by 2, it becomes clear that positive work would translate into an increase in velocity. Using a similar argument, Had the net force been acting against the package's displacement, work would have been negative, which means the final velocity would have to be less than the initial velocity.